Assalamualaikum girls. I am Shamsinisa from Royal Degree College, Chemistry Department. As we are dealing with Unit 4, General Chemistry, in this today we'll see Chapter 5, Photochemistry in this Session 2. We'll study about the absorption of light, consequences of the absorption of light, Jablonski diagram, phosphorescence, photosensitization, fluorescence, and problems. Absorption of light. When a light radiation is passed through a substance, some part of light radiation is absorbed by it. The absorption of light means absorption of quantum or photon. Quantum or photon is a unit of electromagnetic radiation. The energy of each photon is given by E, it is equal to h mu. It is our equation number 1, where h is called the Planck's constant and its value is 6.625 into 10 to the power minus 27 second. Mu is the frequency. We know frequency of light is related to the wavelength. That is, mu it is equal to c by lambda. It is our equation number 2. From equation 1 and 2, E it is equal to hc by lambda. It is our equation number 3, where c is called the velocity of light and lambda is the wavelength. Sometimes energy of a photon is expressed in terms of wave number. Wave number is defined as the number of wavelength per centimeter or per meter in SI units. Mathematically, mu bar it is equal to 1 by lambda. It is our equation number 4. So lambda it is equal to 1 by mu bar. From equation 3 and 4, E it is equal to hc by lambda. That is our equation 3, isn't it? So in place of 1 by lambda, we are writing its value as mu bar. That is 1 by mu bar. So E it is equal to hc mu bar. Consequence of the absorption of light. The primary effect in all photoprocesses is either the increase in the thermal energy of the system or the excitation of atoms or molecules. Excitation of atom is predominant. Primary process. A is an atom. It is absorbing a light, that is h mu. It is being excited after absorbing the light. So we are getting A star, that is nothing but excitation of the atom. Electron spin multiplicity. So ordinary organic molecules contain even number of electrons, and most of the electrons are paired in the ground state. Molecular states with all electron paired in a molecule are called singlet states. That is, the spin of the electron in the excited state is antiparallel to that in the ground state. On the absorption of light, the initial change is the excitation of electron without any inversion in the spin of the electron. This is called singlet excitation. Singlet excited state may undergo spin inversion, giving rise to triplet state with 2 unpaired electrons. Molecular states with 2 unpaired electrons are called triplet states. That is, the spin of the electron in the excited state is parallel to that in the ground state. Singlet states do not split in a magnetic field, whereas triplet states split into 3 different energy levels. Free radicals that have 1 unpaired electron give rise to 2 energy levels in a magnetic field, and so they are known as doublet state. Electronic transitions between the states of the same multiplicity are spin allowed. Example, singlet-singlet transition, triplet-triplet transitions. They are spin allowed transitions. Then the transitions between states of different multiplicity are spin forbidden. Example, singlet-triplet transition, triplet-singlet transition. Now Jablonski diagram. Here the Jablonski diagram shows the various excited states and the various transitions of the molecule. On absorption of light, the electron of the absorbing molecule jump from the ground state, that is S0 to S1, S2, S3 and and so on up to Sn times singlet excited states, depending on the energy of photon absorbed. Here you can see the figure. After absorbing the energy, electron is being excited from ground singlet state to the second singlet state. Here photon absorption. After absorbing the photon, it is showing the excitation. Okay. Then from S to singlet second excited state, it is coming to the singlet first excited state. Here IC, that is nothing but internal conversion, you can see. And from the singlet first excited state, it is coming back to the ground state, that is singlet ground state. Here F it is represented as, that is nothing but fluorescence, that is emission of light will take place. And from singlet excited state, first singlet excited state, the electron is moving to the triplet second excited state. Here ISC, that is, it is showing the intersystem crossing. Then from triplet second excited state, it is coming to the first triplet excited state, that is IC. Again it is mentioning here as IC, that is nothing but internal conversion. And from triplet first excited state, coming back to the singlet ground state, that is represented as P, which is nothing but phosphorescence. For each singlet excited state, S1, S2, S3, there is corresponding triplet state, that is T1, T2, T3. If the molecule, whether it is a singlet or in a triplet state, called as excited or activated. While returning to the ground state, the following processes may occur. The first one is type 1 non-radiative transition. Next is type 2 radiative transition. First of all, we'll see about type 1 non-radiative transition. These are of two types, internal conversion, and second one is intersystem crossing. Now we'll talk about internal conversion. This transition involves the return of the molecule from the higher excited states like S2, S3 or T2, T3 to the first excited state, that is S1 or T1. These transitions are non-radiative transitions. The energy of the activated molecule is given out in the form of heat, but not in the form of light. So this is called as internal conversion and occurs within 10 to the power minus 11 seconds. These can be observed spectroscopically. Then second type is intersystem crossing. It involves the transition between the states, that is between singlet state to triplet state, that is transition between direct spins, parallel, anti to parallel, that is from S2 to T2 and S1 to T1. These transitions are forbidden spectroscopically, but they do occur slowly. Then next type is type 2, which is radiative transition. It involves from S1 and T1 states to ground state. So it is accompanied by the emission of radiation, and these are allowed transition spectroscopically. The transition from S1 and S0 occurs very fast and occurs within 10 to the power minus 8 seconds. This transition or this emission of light is called as fluorescence. The transition from the triplet excited state to ground state is slow and it is forbidden. This is called as phosphorescence. Lifetime of the excited state is more than 10 to the power minus 3 seconds. Why? Because in this inversion of spin takes place, which needs time. In both these cases, the light emitted is of lower energy than the light absorbed, as part of the radiation is converted into heat in non-radiative transition. Now we'll talk about phosphorescence, the phenomenon in which substances absorb light and emit it for quite some time, even after the incident light is cut off, is called phosphorescence. The substance exhibits this phenomenon is called phosphorescent. Now we'll see the explanation. If the substance absorbs light, as a result, the electron goes to higher energy levels. Excitation occurs too rapidly. The spin of the electrons changes and forms singlet state S1 or triplet state T1. The de-excitation of electrons from singlet state S1 to ground state S0 takes place is fast. But in the case of triplet state T1, it is very slow process. So in this process, light emission continues for some times, even after incident light is cut off. Example is sulfides of zinc sulfide, alkaline earth metals containing heavy metal sulfides. Then we will see the applications. These are used as luminous paints for painting watch dials, electric switches, etc. Here you can see the figure as we are talking about the phosphorescence, ground singlet state, that is S0. From that, absorption of a light means electrons, it is going to absorb the light. So now the electron in the ground state, which is present in the ground state, after absorbing the light, it is moving towards the excited state, the singlet first excited state. And from this, it is going to the higher states also, that is S2, S3. Then from each and every state, it is coming back to the original level. That is, here it is mentioned as from S3 to S2, if it is coming, it is mentioned as internal conversion. Okay, and from S2 it is moving towards the S1, that is again mentioned here as the internal conversion. Okay, and after that here you can see R also, that is relaxation state. And from S1, if it is coming back to the ground state, it is mentioned here as F, which is nothing but fluorescence. And from S1 state, if the electron is moving towards the T1 state, that is it is mentioned as ISC, which is nothing but intersystem crossing. And from T1 again it is coming back to the S0 state, it is mentioned as P, which is nothing but phosphorescence. And from T1 it is moving to T2, from T2 it is moving towards the T3, and from T3 it is again coming back to the T2. So it is mentioned as IC, that is nothing but internal conversion, and from internal conversion it is taking a relaxation state, then coming back to the next energy level. Like that it is happening in the phosphorescence case. Now, photosensitization. In some photochemical reactions, the reactant molecules do not absorb the radiation, but other substance absorbs the radiation and pass it on to the reacting molecules and initiates the reaction. This process is called photosensitization, and the substance which absorbs the radiation is called photosensitizer. Here we can see the example. The first one is dissociation of hydrogen molecule to hydrogen atom in the presence of mercury vapors. See here the reaction. We are taking mercury, okay. Mercury vapors are absorbing the radiations of light or rays, and as a result of that it is becoming activated, and we are getting the Hg+, that is activated form of mercury. Then activated mercury, it is made to react with hydrogen, and we will get mercury plus 2 hydrogen atoms. Another example we'll see, that is the decomposition of ozone to oxygen molecule by chlorine. Cl2, it is reacting with ozone, and we are getting back the chlorine along with that oxygen and one nascent oxygen. This nascent oxygen again it is reacting with ozone, and we are getting the 2 moles of oxygen. Then third example is photosynthesis. The process of conversion of carbon dioxide in water into carbohydrate in the presence of light and chlorophyll is known as photosynthesis. Here you can see the reaction, n number of moles of carbon dioxide, it is reacting with n number of moles of water. The reaction will take place in the presence of light and chlorophyll, and we will get C6H12O6 taken n times. It is nothing but carbohydrates along with n number of moles of oxygen. Here chlorophyll acts as photosensitizer. We'll see the mechanism now. In this reaction, carbon dioxide or water do not absorb light directly. Here chlorophyll absorbs the light energy, and this light energy is transferred to carbon dioxide and water. This process takes place in 2 steps. First step is photoreaction. In this process, Chlorophyll absorbs light energy and gets excited. Now, water molecules absorbs light energy from chlorophyll and dissociated into H plus ions and oxygen. Here you can see the reaction. Chlorophyll are here. Chlorophyll absorbs what? Light energy, that is H and gets excited. It is the excited form of the chlorophyll star. Then this excited chlorophyll, it is reacting with water molecules, two molecules of water, and we are getting the 4 H plus ion, 4 electrons along with that oxygen. Second step is dark process. In this process, carbon dioxide molecule converted into carbohydrates with the help of H plus and electrons. The primary product, formaldehyde, is immediately converted into glucose and other carbohydrates. You can see the reaction here, n number of moles of carbon dioxide reacting with n number of moles of H plus ion and electrons. So we are getting formaldehyde here. So the 6 moles of formaldehyde, it is converted to the glucose, that is C6H12O6. Now we'll talk about fluorescence. The phenomenon in which a substance absorbs light and emits a part of it instantaneously, usually at a different wavelength, is called fluorescence. And the substance itself is called fluorescent. Here you can see the diagram. That is, this is the S0. This is nothing but singlet ground state, singlet first excited state, singlet second excited state. Okay. So when the electron is absorbing the energy, at that time after absorbing the energy, it is going up to the first excited state. That is, it is at the first excited state, the wavelength will be 10 to the power minus 15. Then from the first excited state, internal conversion will take place and it is coming back to the singlet ground state at the wavelength 10 to the power minus 8. Then from the ground state, singlet ground state, when it is moving up to the singlet excited state, then from that side, singlet second excited state. From singlet second excited state, it is showing the internal conversion within a wavelength range of 10 to the power minus 12. And from that side, again, it is coming back to the ground state with the wavelength range of 10 to the power minus 8. Now we will see the problems. First problem is, here is asking to calculate the value of Einstein's energy for violet light of wavelength 4000 degree angstrom in kilocalories. Solution is, given data lambda value, it is given as 4000 degree angstrom. If the value of lambda is given in degree angstrom, we are using this formula. That is, E, it is equal to 2.86 into 10 to the power 5 divided by lambda. Here we are calculating the value of Einstein's energy in kilocalories by utilizing this formula. Now we are keeping the value of lambda here in this formula as 4000. Rest of the things are as it is. Now we are simplifying this 4000. It can be written as 4 into 10 to the power 3. So now this 10 to the power 3 from denominator, when it is moving towards the numerator, it will become 10 to the power minus 3. Rest of the things are as it is. Now 2.86 divided by 4. If we are dividing these both values, we get 0.715. Then 10 to the power 5 into 10 to the power minus 3. 5 minus 3, you will get 2, 10 to the power 2. Then the 10 to the power 2 is nothing but 10 into 10, 100. So 100 multiplied with 0.715, so you will get the E, that is value of Einstein's energy, you will get as 71.5 kilocalories. Next problem we'll see. Calculate the Einstein's of energy for red radiation of wavelength 7500 degree angstrom in calories, in joules, in electron volt. Given data is lambda value is mentioned as 7500 degree angstrom. Convert degree angstrom to meter first. So whatever the value will be there in the degree angstrom, it should be multiplied with 10 to the power minus 10. So it will be converted to the meter. Now we are simplifying 7500. 7500 means 75 into 10 to the power 2. So 10 to the power 2, 10 to the power minus 10. We are subtracting. So we will get 10 to the power minus 8. That is, value will be 75 into 10 to the power minus 8 meter. Now energy in joules per mole. For that we are using this formula. E is equal to NHC. N is the Avogadro number, its value is 6.023 in 10 to the power 23, and H is the Planck's constant, its value is 6.625 in 10 to the power minus 34, and C is the velocity of light, its value is constant. All these values you should remember because all these values are the constant values. So for the C value, that is the velocity of light, its value will be 3 into 10 to the power 8 divided by lambda. Lambda just now we have calculated in meter, that is 75 into 10 to the power minus 8. Now what we are doing, we are multiplying these things. 6.023 into 6.625 into 3, whatever we will get the value, it should be divided by 75. So you will get 1.596. Then 10 to the power 23, 10 to the power 8. So how much it will be? 23, 24, 25, 26, 27, 29, 30, 31. 31, 10 to the power 31, 10 to the power minus 34. So how much you will get the value? 31 minus 34 means you will get the value 3. That is minus 3. That 10 to the power minus 8 from denominator, when it is moving to the numerator, it will become 8. 10 to the power 8. So minus 3 plus 8. How much you will get the value? 5. That is 1.596 in 10 to the power 5 joules per mole. Then energy in calories per mole. For that we are going to calculate E. It is equal to the value of E in joules per mole is 1.59, isn't it, in 10 to the power 5. When it is to be converted to calories per mole, we should divide this value by 4.2. So you will get the value as 0.38 in 10 to the power 5 calories per mole. It is the value of Einstein's of energy in calories per mole. Now, as this particular 0.38 is there, now this point if you are bringing one digit towards right hand side, at that time 10 to the power 4, one digit will decrease here. So you will get the E value as 3.8 in 10 to the power 4 calories per mole. Now energy in kilocalories per mole. So whatever the value we are getting in the calories per mole, it should be multiplied with 10 to the power minus 3. At that time, you will get the energy in kilocalories per mole. So you will get the value as 10 to the power 4 into 10 to the power minus 3 means you will get the value as 10 to the power 1, isn't it? So it is nothing but 10. We are multiplying 3.8 with 10, you will get the value as 38 kilocalories per mole. Now energy in electron volt. So 1 electron volt, it is equal to 23.06 kilocalories per mole. Now E, it is equal to this value we are writing, which is in that kilocalories per mole. It is to be converted to the electron volt. So we are taking 38 divided by 23.06. So you will get the value as 1.65 electron volt. That is E value. Now the next problem we'll see. Determine the value of Einstein's corresponding to the radiation of 7000 degree angstrom. So the solution is given data. Lambda value is mentioned as 7000 degree angstrom. So this formula here we are using, that is E, it is equal to 2.86 into 10 to the power 5 divided by lambda in kilocalories per mole. Okay. So lambda, the value of lambda we are mentioning here, that is 7000. Then we are simplifying this value. We can write like this 7 10 to the power 3. So this 10 to the power 3, when we are bringing to the numerator, it will become 10 to the power minus 3. Now 2.86 into 10 to the power 5 into 10 to the power minus 3. So 5 minus 3 you will get 10 to the power 2. Now rest of the things are as it is. Now 2.86 divided by 7. If you divide this value, you will get, if you divide this value, whatever you will get the value, it should be multiplied with 100. By 100 because here 10 to the power 2. 10 to the power 2 is nothing but 100. As a result of that, we will get the value of E as 40.86 kilocalories per mole. Thank you for listening my lecture. With this, our paper 5 syllabus is completed.